Welcome back to Wood Engineering. I'm Jeff Barochko from Carleton University, and in this video, I'm going to be doing a full beam design example. So we're going to start with some design requirements. We are going to select a beam, and then we're going to go through and check all of the applicable resistances. Moment resistance, shear resistance, bearing resistance, compression perpendicular to grain, and also deflection. So let's get started. So these are our requirements for this beam. We're designing just a simply supported beam under standard load duration, dry service conditions. This is an interior beam, most likely. I've given a lateral support to the top beam edge, which is something that we're going to use in our moment calculation. And I've specified that we're going to use Douglas fir larch 20Fe grade glulam. Why the 20F-E grade instead of the 20F-EX grade? Because this is a simply supported beam. It's only bending downward in one direction, so we don't have any kind of negative bending or anything like that. So the 20Fe will be cheaper, and it only has the strong plies on the bottom side. And then I've given loads. So we're going to skip the load combination step here, and I've just kind of given some governing load combinations to save some time in this example, since we've seen all this load combination stuff before. So we have effectively a factored load of 27.1 kilonewtons per meter along the length of the beam, which is a line load. I've already stated above that this factored load is associated with a standard load duration, so that's KD equals 1. And I've also provided the unfactored specified load, and we're going to use that for calculation of deflection, since deflection is a serviceability criteria where we don't factor up the loads. Oh, I also have to provide the beam spacing. No, I do not, because I have the beam spacing, but the span is equal to 7.5 meters. So it's quite a long beam. Okay. Let's see, am I going to need the spacing? I'm going to put the spacing in here too. So these beams are spaced apart. So there might be multiple beams, and they're spaced apart by 5 meters. Okay, but anyway, I'm given the line loads directly, so may or may not need this beam spacing. But what this does mean that even though we have multiple beams all lined up, they're far enough apart that we're not going to be able to apply a system effect factor or a system factor. Okay, so given these information, we can lay out what our modification factors are, and this is a pretty simple case. KD is 1 because of standard load duration. KH, as I said, is going to be 1.0 because these beams are spaced very far apart. They're not close together. All of our KS factors, our service condition factors, are going to be 1.0 because we have dry service conditions. So that goes for bending, shear, SCP, which is compression perpendicular, and KSE, which we would apply to deflection calculations. And we don't have any compression load in this beam because we have not covered beam column design yet. It's untreated, so KT is going to equal 1.0 as well. Okay. So now that we know the loads, we can go directly to calculate what is the moment effect and the shear effect. So this is a simply supported beam with a uniform load. So our factored moment is going to be WL squared over 8, which is an equation that you should tattoo on your arm as a structural engineer. Moment in a simply supported beam. VF, our shear, is just a WFL divided by 2. And that is going to equal, in this case, 101.6 kilonewtons. Okay, so now we're ready to start to, actually, let's get our Glulam properties as well first. Okay, so remember this is Douglas fir larch 20F-E. So we are going to go to the Glulam strength table here and pick out, okay, we have Douglas fir larch 20Fe. So what are the things we're going to need? We're going to need bending moment positive. We don't have any negative bending. So we're going to need this one, bending moment positive. We're going to need a longitudinal shear. We're not going to need compression parallel, but we will need compression perpendicular, okay, for our bearing supports. We are going to need our modulus of elasticity. Okay, and we'll see what we're going to do with bearing when we get there. But for now, we're going to write down all these numbers. So I'm just picking them out from the table, 25.6, 2, 7, and 12,400. Okay, so we have FB. So those are all our values from the table, and we have to remember that when we're calculating deflections, we need to use ES, which is just our E times our KSE times KT, which are our factors that modify our strength for service condition and treatment. And since both of those are 1, then we're going to get 12,400 for this as well. Okay, so now we can start defining our requirements for the beam so that we can go ahead and pick a section. So we already know our moment and shear at the top there, MF and VF. For our beam, the one thing that we still need to know is our deflection criteria. And for bearing, what we're going to do is basically just define what is the minimum bearing length that we're going to need to support this beam, since we don't really have any other information about how the beam is going to be supported. So we're doing that in design. We're going to say, okay, this is how much bearing length I need. And so when I set up the support for this beam, that's what I'm going to have to provide. Okay, but since we already know MF and VF, then I'm going to start with defining the deflection criteria. Because if I can figure out what my deflection criteria is in terms of ESI, that is our Young's modulus times our moment of inertia, then I will be able to pick a beam on that basis. So I can say, okay, this beam needs a minimum ESI of XYZ. So as long as I pick a beam that meets that criteria, then the beam will meet the deflection criteria. So let's start with that deflection criteria. Okay, so here's my deflection criteria of L over 180 for the total load. And I get here L divided by 180, L is 7,500 millimeters, and I get 41.7 millimeters. So that's the maximum deflection that my beam can undergo, according to the requirements of the standard. So then I'm going to calculate, just like before, my ESI required, which is just a rearrangement of my deflection equation for a simply supported beam with uniform load. And if I have different loading condition or different support condition, then I'm going to obviously have to use a different equation here. But this one we are well familiar with, 5WL4, WL to the 4, divided by 384 times delta limit. So this is a rearrangement of the equation that delta is 5 over 384 WL to the 4 over EI. So if I do this and I sub everything in, I am going to use here my specified load because we're talking about deflection. So I'm not going to use the factored load. I am going to use this one here. Okay, so that's 19.7. My L is 7,500 millimeters to the 4th, divided by 384 times 41.7. And if I do that, I get a required E times I of 19.5 times 10 to the 12 Newton millimeters squared. Or I could say 19,500 times 10 to the 9 Newton millimeters squared. So this just depends on what we're looking for in our table. Okay, and this is the number that we're going to look for. As long as we pick a beam that has a higher ESI than this, then we're going to be good to go. And in the tables, it's given as ESI. I could just as easily divide this by ES because I already know what my ES is, and then search for a beam that has an appropriate I. In this case, for the design tables, it's more convenient to do it this way. Okay, so now we're going to move to bending resistance. We're going to pick our beam. Actually, let's pick trial beam first. Let me see. Yep, okay, so let's pick a trial beam first. And our criteria are, again, that MR is greater than MF, which is 190.5 kilonewton meters, and that our VR is greater than our VF, which is 101.6 kilonewton meters, and that our ESI is greater than 19,500 times 10 to the 9 Newton millimeters squared. So we're going to basically go to our table and search for these. Now, let's start by looking at the requirements for the table. So if I go to the checklist, here is the wood design manual. And in the wood design manual, it has a checklist before it gets to the design tables. And this checklist tells you exactly what are the requirements of the beam in order for you to be able to pick it straight out of the table. Now, if it doesn't meet these requirements, it doesn't mean that you can't use those tables. It just means that you have to be a bit careful about how you select your values. So for straight glulam beams, which is what we're designing, for straight glulam beams, is the beam subject to positive bending moments only? Check. Load duration is standard? Check. Surface conditions dry? Yes. We don't have any KT, that's check. Does construction provide lateral stability for the beam? KL. Okay, so this one is a question mark because we know that we have purlins that restrain the top of the beam every 2 meters. That was given in the question. So I have my beam, you know, it's 7.5 meters long, and at a 2 meter spacing, there are some purlins on top that are going to restrain the lateral deflection and prevent lateral torsional buckling. But is that going to be adequate to totally restrain the lateral torsional buckling? We don't know at this point because we haven't done the check to see what KL will be. So this one right now is kind of a question mark. We don't know if our KL is going to equal 1.0 or not. So this is something that we're going to assume right now, and then we're going to check it when we actually do our beam design check. So let's say yes for now. And if it turns out that it's no, you know, one of my options if I was doing an actual design would be to change the purlin spacing in order to make this correct. Or if not, I could just pick a larger beam if I need to. So we're going to assume that this is the case for now, but we're going to make sure to circle back and make sure that it's the case after we pick a section. Is size factor applicable? Yes. Is the beam free of notches? Yes, that's true. So we don't have any notches in this beam. For an example of how to design with notches, I've done a separate example. And is the beam simply supported and the loading uniformly distributed? I mean, it is in this case, but this is for the check where we are looking at WR, which is the detailed design check. We're going to do that one by hand to check it. So right now I'm just going to look at the regular VR because this beam should be small enough that it is less than 2.0 meters, meters cubed of volume. Okay. So, you know, if the answer to any of these questions is no, you know, look at the modification factors and make necessary adjustments to the tabulated resistances and EI values. So let's say my KD was 0.65 instead of 1. That means that the strength values in the table should be divided or should be multiplied by 0.65, right? And that will give me the actual strength for a KD of 0.65 because the table values all assume that KD equals 1. Alternately, what I can do is on the other side of the equation, the factored moment, you know, my target factored moment, I could divide that value by 0.65, which will raise the target, which means that when I look in the table, I'm going to pick something that has a higher strength than I would if KD equals 1. So those are two ways to approach if I have different assumptions than are in this table. So in this case, we're a little bit lucky because we satisfy all these criteria except potentially KL. And again, we're going to come back and check later to see if that's actually the case. Okay, so let's go to the table, the appropriate table for Glulam. Okay, so I'm just going down, 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 down. It starts with the beam selection for sawn timber, and now we have the Glulam selection table. Okay, so our stress grade is 20 Fe in a Douglas fir larch. So you can see here we have the MRs, we have the VRs, and we have the ESIs listed right here. So recall our MR was 190.5, so none of the 80 millimeter glulams are going to do the trick. So let's go up to the next size, 130 millimeter wide pieces of glulam, and read down until we get something that is greater than 190. And you see we get one right here, 130 by 646 is just greater than 190. It's 208. So this is the first one that exceeds 190. Okay, let's move over and check our shear, which is this column. And we have 101, and our shear resistance required is 101.6. So I am going to go forward with this. Why? Even though it's right on the edge? Because I have some ways to juice this number a little bit, which we saw before. So this is the simplified shear calculation. I know that I have some options to get a higher shear resistance, effective shear resistance. For example, I can look at my VF at D from the support instead of looking at VF at the support. So the VF that we have here, this VR, which comes from our VF that we calculated here, this WL over 2 value, that's the VF at the support. And remember that for longitudinal shear design, we can look at VF at D away from the support, which is going to reduce that number. So my true design number can actually be a little bit less. Okay, so coming back here, coming back to this one, we're looking at this 130 by 646. So MR is okay. VR is mostly okay, and we think we're going to be able to satisfy that number. And this is the ESI. And if you look up here, the ESI is in times 10 to the 9 Newton millimeter squared. And ours was, down here, the requirement was 19,500 times 10 to the 9 Newton millimeters. Oh, sorry, Newton millimeters squared. Okay, so coming back here. So we're looking for a value of 19,500 at least here. And you can see that our 130 by 646 more than satisfies that, 36,200. So we're more than double over. So it's going to be fine. So let's try this section. We're going to check all the resistances and make sure it works. And in particular, we're going to be concerned about the KL, that it is adequate, the lateral support condition. And we're also going to want to make sure that we can get a VR that's going to satisfy our VF of 101.6. Okay, so let's choose from the selection table, try 130 by 646. Okay. So we're going to start by looking at the bending resistance of this. Okay, so just laying out the geometry of the beam that we've selected, B is 130, depth is 646. I've calculated my I manually and checked manually the ESI just to do a sanity check. I mean, this is the number that we got out of the table for this beam, and everything seems fine. So we're satisfying our deflection criteria. So that's great. So deflection equals, deflection is okay. All right, we're also going to need our S, which is BD squared over 6. This is our section modulus. And we're going to get this for our section modulus. Okay, so now we can start looking at our bending resistance. Recall our bending resistance for Glulam has two different criteria. We have MR1 and we have MR2, and they look like this. One check that uses the KZBG, and one check that uses the KL. So we're going to have to calculate all these parameters and plug them in. And remember that it's the minimum of these two that governs the strength in bending for Glulam. Minimum of these. Okay, so first of all, our phi is a 0.9 for this equation. And our FB, capital FB, is small fb times all our modification factors. And those are all 1. So we have 25.6 times 1 times 1 times 1 times 1. And so our capital FB is also 25.6 MPa. Okay, S we already calculated. Kx, which is our curvature factor, is 1.0 since this is a straight beam that we're designing. And now we have to calculate KZBG and KL. Okay, so you recall that KZBG is kind of a complex equation. I'm going to write it out here. Okay, remembering that all of these inputs have to be in millimeters, the B, the D, and the L. And the interesting thing here is that you can see that our KZBG, in this case, we're pretty close to the baseline beam size that they used in developing KZBG, which was a 130 by 610 by 9100. So we have here a 130 by 646 by 7500. So we should expect our KZBG to be pretty close to 1, and it turns out that it is. It's 1.014. This must be less than 1.3, which it is. So we're okay. We're not going to cap it off at 1.3. Okay, so that's our KZBG. Now we have to find our KL. And so remember, for KL, we first have to find our effective length, which starts with an unsupported length. And then we have to find our slenderness factor for buckling. Then we have to compare it against a criteria to see which bin we fit in, which kind of lateral torsional buckling we have, either no lateral torsional buckling or an intermediate inelastic lateral torsional buckling or completely elastic lateral torsional buckling. Then we can calculate our KL. So the first thing is that we need to find our unsupported length. So that is going to be LU here, which for when we have purlins, it's the purlin spacing, and that is called A, and that for us is 2000 millimeters. Okay, now we need to calculate our LE, which we get from a table, which you will recall looks like this. Okay, so we have our effective length factor, which depends on whether we have intermediate support or not. In this case, we do have intermediate support, which are our purlins. We have uniformly distributed load. So that means our LE is going to be 1.92 times A. So coming back here, our LE is 1.92 times A, which comes out to 3,800 millimeters. Okay, so now we can calculate our CB, which has this equation. And if I calculate all that out, 3,800 times D is 646 divided by B squared. And I sub all that in and I get 12.1. Now you remember that the requirement for us having no lateral torsional buckling is that CB should be less than 10. So we are at 12.1, which means we do have some reduction to account for inelastic lateral torsional buckling, or the intermediate case of lateral torsional buckling. So that means that our KL is not necessarily going to be 1. So the assumption that we made that KL equals 1 may not be true. So we might have to actually modify And if we did have to modify, what we'll do is come out with our KL, and then we'll see how much the reduction would be. And then we can go back to the table, divide our factored moment by that reduction to factor our moment up, and then pick a new section. We're going to see if that's necessary, because 12.1 is awfully close to 10, so it could be that our reduction is not that great. Okay, so in order to figure out that reduction, we have to check if we're in the inelastic region or the elastic lateral torsional buckling region, which is what this CK factor does. Okay, so when I calculate out CK, I get 21.7. So if my CB was above 21.7, that would mean I'm in the elastic lateral torsional buckling region. And so I am in this, I'm in the kind of intermediate region then, because CB is between 10 and CK. So therefore, my KL is going to be this equation. And I get KL equals 0.967. Well, awfully gee, that is pretty close to 1. So probably we're going to be okay with the trial section that we picked, because we had a little bit of space. It was, I think our trial selection, we were going for 190.5, and I think our strength was 200 something. So probably we have enough room that we're going to be fine. But that's easy to check. All we got to do is plug in our MR calculations. So this is the first one. That's phi. FB is 25.6. Then we have S, which happened to be 9042 times 10 to the 3. That's millimeters cubed. As always, be very careful with your units. KX is 1.0, and KZBG we determined was 1.014. Now this KZBG, that is included in the tables. So we don't have to worry about, if KZBG came out to be quite a bit less than 1, that's fine, because the selection tables include KZBG in there. Just what they don't include are KL. So let's do this calculation again. And 25.6 and 9042 times 10 to the 3. And KX is 1, and our KL is 0.967. So obviously the KL1 is going to govern, but here are the two strengths. And this one is 201.5 kilonewton meters. That's probably too many significant figures. Probably 3 is enough here. But therefore, the governing moment strength is the one that includes KL, and that happens to be greater than our MF, which was 191 kilonewton meters. So we're okay. Good to go. All right, so what did the table say that it was? Let's go back and recall. So if I go back to the table, the selection table, we had 130 by 646, and it was supposed to be 208. And because we had a KL that was a little bit less than 1, it went from 208 to 201.5. No problem. Still plenty of room. Okay, so I'm going to put a cut in the video here, and in the next part, we're going to continue this example and look at shear resistance and then bearing resistance.